Order of a reaction is defined as the sum of powers to which the concentration terms are raised in a rate law expression. It is an experimental value. The rate is directly proportional to the molar concentration of the reactant. That is called as a first order reaction. Now the overall rate of the reaction is determined by the slowest step in the reaction, which is called as the rate determining step. Hello everyone, this is Ambali Unnikrishnan from the Department of Chemistry. So today I am back with session 2 of the chapter Chemical Kinetics. So in the last session we studied what we are going to study under chemical kinetics, right? As well as we studied about what is rate of chemical reaction, what is average rate, what is instantaneous rate, as well as different factors which affect the rate of the reaction. So how the rate of the reaction depends upon the concentration we studied using rate law or rate expression, right? Also, we studied what is rate constant of a reaction and the characteristics of rate constant. So, in today's session, we are going to study what is order and molecularity of reaction. Okay, so first let us begin with order of a reaction. So, let us understand from the definition itself. Order of a reaction is defined as the sum of powers to which the concentration terms are raised in a rate law expression. It is an experimental value. So, you know already, that is from the last session itself, how to write the rate law or rate expression. Right. For example, we have taken here the rate expression. Rate is equal to k into a to the power x into b to the power y. So, the concentration terms are raised to some powers which may or may not be equal to their stoichiometric coefficient, right? We have already discussed this. So, the sum of these two powers will give you the order. That's it. So, order is the sum of the powers to which the concentration terms are raised in a rate law or rate expression. So, this x plus y will give you order. So, it is an experimental value, okay? Just from the balanced chemical equation we cannot write it. It is an experimental value. Okay. So order can be 0, 1, 2, etc. and even fractions also. Applicable to both elementary and complex reactions. So elementary reactions, what are elementary reactions? Those reactions which takes place in only a single step. Okay, and complex reaction means it takes place through a sequence of elementary reactions. That means many steps will be there. Elementary means single step reaction. Complex reactions means of course there will be more than one reactions which is present, or else you can say that is a sequence of elementary reactions will be there. So what is order? It is a sum of the powers of the concentration terms. Okay, so this x plus y will give you an order and this is an experimental value. Clear? So it can be 0, 1, 2. Or else fractions also. Now, based on this, you have zero order reaction, first order reaction, second order reaction, etc. So, in this chapter, we are going to study in detail about zero order and first order reactions, right? So, beginning with zero order reaction, the rate of the reaction is independent of the molar concentration of the reactant. So, what does that mean? Rate is equal to k into a to the power 0. This is a rate law or rate expression, right? So, here you can see the molar concentration of the reactant is raised to the power what? 0. So, in that case, what is the order of the reaction? The order of the reaction will be equal to 0, right? So, such reactions are called as zero order reactions, wherein the power will be 0. So, if any concentration term or any term raised to the power 0 will be equal to what? It will be equal to 1. So that means rate is equal to k into a to the power 0 means what? Rate is equal to k, right? A to the power 0. This part will become 1. So rate is equal to k. So that is what is written in the first sentence. The rate of the reaction in zero order reaction, it is independent of the molar concentration of the reactant. Is the rate depending upon the molar concentration? No, right? So that is called as a zero order reaction. It does not depend upon the concentration of the reactant. It only depends on rate constant, not on the concentration of the reactants, because the power is 0 in this case. So, for example, 2 moles of ammonia, it breaks down to give nitrogen and 3 moles of hydrogen gas. So, the rate expression is rate is equal to k into molar concentration of ammonia raised to the power 0. So, here you can see the coefficient is 2. But still, the order of the reaction is zero order reaction. So, as it is to raise to the power 0, it means that this particular term is equal to 1. So rate will be equal to what? K. So that means that here the molar concentration of ammonia is not a factor of the rate of the reaction. So such reactions are called as zero order reactions. Now moving on to the next one, that is first order and second order reaction. The rate is directly proportional to the molar concentration of the reactant. That is called as a first order reaction. So what you can write, rate is equal to K into A to the power 1. Right. So in that case, what is the power of the molar concentration term here? It is 1. So what is the order of this reaction? Order of this reaction is 1. So in this case, can you tell it is independent of the concentration? No, right? Rate is equal to K into molar concentration of A. Right. So in that case, the rate is directly proportional to the molar concentration of the reactant. So if I am removing this constant from here, what you will get? Rate is directly proportional to the concentration of A. So that is what is written here. Right. So here is an example of ethene reacts with hydrogen, that is hydrogenation process happens and forms ethane. So here you can see rate is equal to K into molar concentration of ethene. So you can see it is raised to the power 1. So this is a first order reaction, and in here rate of the reaction depends upon the molar concentration of ethene which is taken. Now moving on to next one, that is second order reaction. The rate is directly proportional to the square of molar concentration of the reactant. Here it is square. How is that coming? Rate is equal to K into A to the power 2. So A to the power 2 means what? It will be order of the reaction will be 2. Order of the reaction will be 2. So again you can also write it as rate is directly proportional to the square of molar concentration of the reactant, right? So that is what is written here. Now 2NO2 gives 2NO plus O2. Herein rate is equal to K into molar concentration of NO2 raised to the power 2. So you have 2 here. This is the order of the reaction. So rate is directly proportional to the square of molar concentration of the reactant. So this is zero order, first order and second order reaction. I hope it is clear. Now moving on to the next part, that is molecularity of a reaction. Right. So it is the total number of reacting species taking part in an elementary reaction which must collide simultaneously to bring about a chemical reaction. So it means that it is molecularity, it is the total number of reacting species, right? It is the total number of reacting species which is taking part in an elementary reaction which must collide simultaneously to bring about a chemical reaction. So in a chemical reaction, how many number of species are involved in the formation of the chemical reaction is called as the molecularity of reaction. So let's take an example, AA plus BB giving CC plus DD. So in here, what is the molecularity of the reaction? That will be this small a plus small b. So A plus B will give you the molecularity of the reaction. That is how many number of reactant species are there, right? So A plus B, these are the number of moles. So A plus B will give you the molecularity of the reaction. Now, molecularity, it is a theoretical quantity. That means if you have a balanced chemical equation, from that itself you can directly calculate the molecularity of the reaction. So what you have to remember, order is an experimental value and molecularity is a theoretical value, and it cannot be a fraction or 0. It cannot be fraction, half molecule, we can't say, right? So it can't be a fraction or it can't be 0 also. 0 means, of course, the reaction is itself not taking place. There are no reactants, means how will the reaction take place, right? So molecularity above 3 is very rare because collision will not be effective if the number of molecules is greater than 3. Okay, so molecularity, that is number of reacting species, can be 1 or 2. Maximum it can be 3. More than 3 it is not possible because effectively the molecules will not collide and you will not get the product. Okay, so it cannot be fraction, it cannot be 0 and it cannot be more than 3. So this is called as molecularity of a reaction. Okay, so now the overall rate of the reaction is determined by the slowest step in the reaction, which is called as the rate determining step. So what does this mean? As I told you, molecularity of a reaction, in an elementary reaction, we can say how many reacting species are there. If there is more than one step, that is if it is a complex reaction, more than one elementary reactions are there, then in that case, the overall rate of the reaction is determined by the slowest step in the reaction, which is called as the rate determining step. So there will be 1 or 2 or more than 2 steps will be there for that reaction. So in that case, which is the step? So which is having the slowest rate, that will be called as a rate determining step, right? Example, the decomposition of hydrogen peroxide catalyzed by iodine ion in alkaline medium. So H2O2 that is hydrogen peroxide, it decomposes to form water and oxygen in presence of iodine, right, catalyzed by iodine ion. So the reaction takes place in 2 steps. First you have hydrogen peroxide reacts with iodide ion to form water and IO minus, and then again this hydrogen peroxide is going to react with IO minus to form water, iodide ion and oxygen gas. So there are 2 steps which you can see. This is not a single elementary reaction. There are 2 steps which is involved. So out of these 2, the slowest step will be the rate determining step. Okay, I hope that is clear. Now let us differentiate between order and molecularity, what we have studied till now. So order is a sum of powers to which the concentration terms are raised in a rate law, right? So if you have rate is equal to K into A to the power X into B to the power Y, then X plus Y will give you what? X plus Y will be the order, right? Now molecularity is the total number of reacting species taking part in an elementary reaction. So if you have a reaction A plus B giving C, so in that case what will be the molecularity of the reaction? You have 1 here, 1 here. You don't have to consider the product, right? Only reactants you have to consider. So the number of moles here is 1, here it is 1. So what will be the molecularity? Molecularity will be 2. Right. Now, it is an experimental quantity, right? Order is an experimental quantity. Just by looking at the balanced chemical equation, you cannot determine it. Now, theoretical value. Molecularity is a theoretical value. You can obtain it from a balanced chemical equation. Now, order can be 0, fraction or integer, and molecularity, of course, it can't be 0. Now, this can be obtained by knowing the rate law. Now, can be obtained from a balanced chemical equation. You can get it from a rate law, right? But not a balanced chemical equation. Molecularity you can obtain from a balanced chemical equation itself, right? Now it is applicable for both elementary and complex reactions. You can find the order of the reaction, but molecularity you can only obtain for a elementary reaction. For a single step you can tell the molecularity of the reaction. I hope that is clear. Now let us see a numerical based on this. Calculate the order and molecularity of the reaction. It is given A plus B giving product. The rate expression is already given here. So it is simple. You already have the rate expression here. You have the rate expression from which you have the powers also. So what will be the order of the reaction? It will be sum of the powers, that is 3 by 2 plus 1 by 2. What is 3 by 2 plus 1 by 2? It is 4 by 2, that is equal to 2. So what is the order of the reaction? It is a second order reaction, right? Now moving on to the molecularity of a reaction. Molecularity means, or what is the total number of reacting species here. So the reaction is already given here, A plus B giving products here. So what are the number of moles here? 1 and 1. So what is the total number of reacting species here? It is 1 plus 1, which is equal to 2. So this is the order and molecularity of the reaction. This is how you have to calculate, right? Now moving on to the different units of rate constant. So already we have discussed what is the unit of rate in the last session. Now we are going to see what is the unit of rate constant when it is a zero order reaction, first order reaction and a second order reaction. The unit of rate constant is different for different order reactions. So first let us see for a zero order reaction. So what is a zero order reaction rate law? It is rate is equal to K into A to the power 0, right? A to the power 0 means this term will be equal to 1. So what you will get? Rate is equal to K you will get. Right. So in this case, in a zero order reaction, how do you calculate the unit of rate constant? Unit of rate constant will be of course equal to unit of the rate, right? So unit of the rate we have already studied, that is mole, liter inverse, second inverse. So in a zero order reaction, the unit of rate and unit of rate constant is the same, because rate is equal to K. Now moving on to the first order reaction, rate is equal to K into A to the power 1, right? So in that case, A to the power 1 means this A will remain as it is, right? So you have rate is equal to K into A, right? A to the power 1 is A itself. You need the unit for K. So I'll bring it here. So you'll have rate divided by molar concentration of A. So what is the unit of rate? You already know, that is mole, liter inverse, second inverse, divided by what is the unit of concentration term? It is mole per liter or mole inverse you can write. So you have a mole inverse here, you have a mole inverse here, which gets cancelled. So what is only remaining? You have second inverse. So for a first order reaction, the unit of the rate constant is second inverse, right? Now moving on to second order reaction, you have rate is equal to K into A to the power 2, right? So what you have, rate is equal to K into A square. So in that case, again we can take it in the same format. K is equal to rate divided by A square. So rate, what is the unit? We already know, it is mole, liter inverse, second inverse, divided by molar concentration of the reactant. What is the unit of concentration? It is mole per liter, mole liter inverse square you will have. So 1 gets cancelled, and that is 1 mole liter inverse gets cancelled, 1 mole liter gets cancelled. So this mole and liter inverse will go to the numerator. So what you will have? This mole will go to the numerator, you will get mole inverse. Liter inverse will go to the numerator, you will get liter. And second inverse is already there, so you will have this mole inverse, liter, second inverse. That is the unit of the second order reaction. So if you can't remember the unit of each of this rate constant, what you can do is you can remember this formula, that is mole 1 minus n, liter n minus 1, second inverse. So if you remember this, in the place of n, if you substitute, you can directly get the unit of the rate constant. That means, for example, if it is a zero order reaction, if you are substituting in this equation, n will be 0, right? Zero order reaction means n will be 0. So what you will have? Mole 1 minus 0. What is 1 minus 0? 1 itself. So mole raised to the 1 means mole itself. Liter raised to 0 minus 1 is what? Liter inverse, you will get second inverse, right? So that is what you have, mole liter inverse, second inverse. So same way for first order and second order, you can substitute in this particular equation and you can find the unit of the rate constant. Clear? Now we have a question here. Identify the reaction order from each of the following rate constant. So how you can identify the order of the reaction? Just by given the rate constant of the reaction. So one reaction is given 2.4 into 10 to the power minus 5 liter mole inverse second inverse, or else you can also write it down as mole inverse liter second inverse. So just by looking at the rate constant, how can I determine the order of the reaction? I know the unit, right? Rate constant unit. From that itself, I can calculate the order of the reaction. So mole inverse liter second inverse means it is a second order reaction, right? It is a second order reaction. Mole inverse liter second inverse. Now the last one you have is 3 into 10 to the power minus 2 second inverse. Second inverse is the unit for a first order reaction, right? So this is a second order reaction and this is a first order reaction. I hope that is clear just by looking at the unit. So in the next session, we are going to discuss about the integrated rate equation of zero order and first order reaction in detail. That is a very important topic. So I hope the concepts that I've covered in this session is clear for you. So that's all for today. Thank you.